Will I get a round of applause at the end too? That'd be nice.
You get it now.
Now?
Now.
Just based on this. That's awesome. Okay. So something today, I don't know if we'll get through the whole day because apparently my Ed TA Mohammed went through a lot of slides, but we'll get through as much as we can. The test is next Tuesday, and it covers chapters 5 and 11, as well as any review chapters like 1 through 3. Take a look at the syllabus if you're not sure. I would highly suggest to everyone that you read the textbook. The textbook has a whole lot of good information, obviously. That's why we buy it. But today we're going to be covering a little bit further ahead in the course. So guest lecture 6, I'm that guest. Hello. Basic properties of solutions. So when we think of chemistry, like you just picture what happens when we perform chemistry. You usually think of someone, are you raising your hand there?
Yes. Is it possible to turn those?
Oh yeah, sure. Is that better? Okay. So typically, if I picture someone trying to perform some chemistry, I don't usually picture them taking 2 solid blocks and rubbing them together. I picture them mixing some solutions. Solutions are very convenient, and much of chemistry occurs in solution. So when we want a reaction to happen, we in general need 2 things to collide together. Yes, this isn't always the case, but we need 2 things to hit. And for that to happen, it's a lot easier in a solution where everything's rolling on top of each other. Yes, in a solid state, they're fixed in a fixed spot. It's a lot harder to get them together to react. And in the gas phase, yes, you have lots of collisions, but gases can be dangerous in general. We do lots of chemistry with gas phases. I'm just saying it's a lot easier to do it in solution. And so understanding the characteristics of solutions is very important. So for instance, it says here that there's little chance of an uncontrolled escape of reactive chemicals. It's very true. In the gas phase, however, we can sometimes have some accidents. So for instance, and I don't know if you guys saw this in the news recently, you don't have to look in the science magazines to hear about this. This was a giant accident back in 1984 where methylisocyanate was spilled as a gas down in, where was it, Bhopal, India. Thousands and thousands of people were dead. It's because of things like this that we're always questioning, how can I do this chemistry in a safer way? And oftentimes we want to do it in a liquid form. So for instance, we know that North America has a lot of natural gas, yes? We could use it for fuel, but it's very dangerous to transport natural gas. And so we always look for ways on how to convert that to a liquid fuel, like methanol, convert methane to methanol, so that we can avoid accidents. Okay. So solutions can, of course, be dangerous too. I know I've spilt things on myself before, but while there are solutions of gases, uniform composition throughout, and solids, sort of a frozen snapshot of a liquid solution, most solutions are liquids, with a liquid solvent and gaseous, liquid, or solid solute. So if you think about that for a second, that last line, liquid solvent and gaseous, liquid, or solid solute. Hydrochloric acid, you guys usually use it as liquid, right? HCl is actually a gas at room temperature, and we dissolve it into a liquid, usually water, and that gives us the HCl acid that we work with in the lab. So that's actually a solution, right? It's a gas mixed in. Same with a liquid-liquid solution. I could take any liquid, Windex, and mix it with more water. That's a liquid-liquid solution. And a solid with liquid, that would be something like sodium chloride, which is a solid at room temperature in a liquid. So, but a solution is a single phase. If I take sodium chloride and mix it in with some water, I don't see 2 different phases present. That's because the sodium chloride is fully dissolved. So I have one phase, just the solution. So, dissolving sodium chloride in water, it gives us a single phase, like I was saying, up to about 25% sodium chloride. Now that's by weight. So in your first chemistry class, you may remember, and I'm not sure if they do it here at UCI, but they may do a solubility test where you take some water and you put in sodium chloride until all of a sudden it will no longer dissolve the sodium chloride, and then it starts piling on the bottom. That's when it's reached its saturation point. And for water room temperature, that's around 25%. Once no more salt can dissolve, the solution will be saturated. Adding further salt will give 2 phases. The solution, which is full of sodium chloride, and the solid sodium chloride on the bottom. The saturation point depends on temperature, if we think about that just in general, we know that hot solvents tend to dissolve things faster and easier. They can dissolve more material. This makes sense to us. A surprising note here, before this lecture, I thought seawater was a higher weight percent, and just an interesting bit, you know that if you drink seawater normally, you will die of dehydration, and all you have is just that little bit of 3.5 weight percent salt. I thought that was interesting. So, a phase diagram. If a phase diagram is not familiar to you, then you should be reading the textbook more. Okay? This is a basic phase diagram, but instead of pressure versus temperature, like you may have seen, we have temperature versus the weight percent sodium chloride in water. I'm going to go through this slowly. So what we're taking is water at 0% here, no sodium chloride, and then we slowly change to 100%. So let's start over here on the left, where we have 0% sodium chloride. Now, that's just water, right? So at 0 degrees Celsius, just water, well, that's going to be ice. It's going to be frozen. And above that, it'll be just liquid water until you get to 100 degrees Celsius, and then it'll boil. So you probably have seen or heard about when roads freeze over, like in the mountain passes. It's very dangerous to drive over the ice. And so what they'll have is they'll come and salt the roads. You may have heard of that before. What they're doing is putting that salt into the water, and there's a freezing point of depression. So you can see on this phase diagram, let's start at 0%, and then I put in a little bit of salt. All of a sudden, that freezing point starts to lower and lower and lower, down to here. And now I see that I can get all the way down to minus 20 degrees Celsius, and the solution won't freeze. And this is safe for the roads, because when they put that in there, the ice will melt in general, depending on the temperature, and it's a lot safer to drive on the road. It's a good application. So if we start up in here, just as a demonstration, let's say we're at room temperature, around between 20 and 25 degrees Celsius. We know that as we add salt, then it's going to dissolve, yes, until we reach this around 25% by weight sodium chloride. One thing to note here is the bending of this line. So you can see that it's bending slightly to the right, yes? As we increase in temperature, I can see that the weight percent, the total weight percent that I get for liquid solution, before I start getting liquid solution sodium chloride, it starts to increase. This is just a visual application to that thought, where the hotter we hear, the higher temperature our solvent is at, the more we can solubilize that sodium chloride to get a higher percent. But depending on what temperature we're at, we'll pass into this phase, the liquid solution plus sodium chloride. Let me just mix this. So the notation A plus B, this always means two phases. So in this instance, we would have liquid solution as one phase and the solid sodium chloride as another. If we took this liquid solution plus sodium chloride and start to cool it, at one point we're going to get liquid solution plus sodium chloride that's hydrated. It's simple to think of it cooling it down, more material is going to crash out, you're solubilizing less. But as you get down to really, really, really cold temperatures, you start putting that water on sodium chloride. So if we think of this entropically, as you lower the temperature, it's a lot easier to get things to hit together and stick. So that sodium chloride tends to crash into one of those waters, or rather it's water crashing into sodium chloride, and it'll stick. So we get this hydrated form. And as we increase the percentage of sodium chloride more and more and more, we see that we get the sodium chloride 2H2O plus just sodium chloride solid. And that's because if you think of this as a phase diagram, what we're saying is, oh, in this region I have almost no water left, and it's almost all sodium chloride. So why do things dissolve? It's the same reason that gas spreads out. It's to fill a container. It's statistics. It's hard to keep things in one spot. Things like to spread out. So dissolving increases the disorder of the solute. You can think of it just based on statistics, and you don't have to take in a class to just think of it with common sense. So let's look at the statistics with just 6 atoms. We're just going to say krypton, but it doesn't matter. This is just 6 particles. It could be anything. So we're taking 6 atoms of krypton gas in a container, starting with all 6 on one side and the stopcock closed. There's a picture in just a moment. I believe it's next. Yes, it's next here. So imagine we have this scenario where we have 2 containers and there's a stopcock here, so it can effectively block it off. At one point we put 6 atoms, which of course just mentally that's an obscurely small amount of atoms. This is just a demonstration. 6 atoms of krypton on one side. And then we open the stopcock. We know, just from common sense, that that's going to equilibriate until they're on both sides. So why does this happen? Why does the pressure equalize? It equalizes because this is the most likely outcome. If I go back for a moment, there we are. If I go back for a moment and take the moment when there are 6 atoms of krypton, and then I open the stopcock, what's going to happen? So I've got 6 atoms that are just crashing around all over the place, and I have an opening. Naturally, since there's nothing here, it's a vacuum, those are going to statistically start bouncing over onto the other side. And then once I get onto the other side, they're also going to have a chance of bouncing back, until, of course, I reach this final state where it's equal on both sides. Now, this is an example with only 6. What are the chances of it not being equal on both sides? So here, we've taken these atoms and we've colored them. Again, these are just krypton. They're just colors, so you can see a difference in individual atoms. So we take these 6 different colors of krypton, and this is a certain configuration. It's one possibility. And when it talks about the weight, this is a statistical weight. It's not mass. This is how much does this particular configuration contribute to the total possible outcomes. And we'll go over the weight in one moment. So we have this scenario where I have 6 on one side. That's a 6-0. So there is only one way to have all 6 on one side, right? That way right there. All 6 colors in one hole. Nothing anywhere else. So moving on, if I change it a little bit and bring over 1, a more even distribution has a higher weight. So before, let me demonstrate, we have a weight of 1 for this configuration. It has one possible way of happening. When I go to just 5 and 1, I see that I have 6 possible ways to do this. The configuration of 5 to 1. Taking any one of these colors, yellow, red, blue, green, sort of blue, magenta, I don't know. Taking one on either side, there are 6 different ways to do this. Just statistical randomness. Krypton on one side, krypton reality not colored. Yeah, okay, already said that. So by the time we get to 4 and 2, there are a whole lot more possibilities. We can take, and obviously I'm not going to go through each one of these, but you can take any combination of these colors with 4 on one side and 2 on the other, and you find that there are 15 different ways. You can see how this grows exponentially, and in fact, it is exponential. Counting configurations. So for the 3 to 3 configuration, there are 20 different ways to color the atoms. The configurations 2 to 4, well, let me go back for just 1 second. So you can imagine that with all these possibilities with 4 and 2, now we move 1 more over. And with 3 and 3, there are 20 different ways to color those atoms, 20 different possibilities. And then we had 2 containers, right? One on the left and one on the right. And we were starting with the one on the left being more filled. If you go to the opposite side, the one on the right being more filled, all the statistics are the same. You're just doubling that possibility. So the configurations 2 and 4, 5 and 1, and 0 and 6 have those same weights as 4 and 2, 5 and 1, and 6 and 0. They contribute just as much. So the total number of configurations that we have is given by 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1 equals 64. You can see what we were doing was starting with 6 and 0, 1, right? 5 and 1, and that contributes 5, and so forth until it's even. And then you can go to the other side. That's how many possible orientations of the system there were, and that's 64 total, which, as I mentioned earlier, no coincidence as being exponential, it's an exponential statistical analysis, 2 to the 6th. The number of containers, 2, raised to the power of the number of atoms. It'll mention in a moment, and I'll just say it now, you can imagine that with 64 and only 6 atoms, just think of how many atoms are in a balloon, right? If those were 2 metal containers and you had an atmosphere in one and then opened it up. If it's exponential like that, the number of possibilities that include atoms mostly on one side, they don't contribute hardly anything at all. It's statistically insignificant. It doesn't matter. And so by the time you get to any sort of significant amount of atoms, there's no point in even considering a situation where the atoms are mostly on one side. They're equal. They will equilibrate. About 50 per 64th of the time, if the atoms are moving randomly, we'll look and see a 4 to 2, or a 3 to 3, or a 2 to 4. And that's just adding up those possibilities, okay, equals up to 50 to 64. And about 14 of 64 times, we'll see that 6 to 0, 5 to 1, or 1 to 5, or 0 to 6. So like I was saying, if we took that 64 and made it 10 billion, right? Avogadro's number, what is it? Times 10 to the 23. That's way beyond a billion. You're talking about huge, huge numbers now. So when we view it this way, the gas is spread out just because it's more likely. When the first scientists started looking at these systems, they didn't have to have the chemicals. They could just envision what's mathematically correct. To first approximations, when you don't consider chemical interactions, math describes almost everything. It goes into physics, it goes into chemistry, it describes the world. It's only when you start taking exact scenarios where you have to start considering how atoms interact together, etc. So it's more likely for them to be found equally distributed and jammed into a smaller volume. Likewise, and again, it's just going back to statistics, if we roll a pair of dice, the most likely outcome is to get a 7. So when we have large numbers of atoms, a nearly even distribution is overwhelmingly likely. Considering the solvent to be like a vacuum and the solute to be like a gas, so consider for a moment if I had a beaker full of water with solid sodium chloride on the bottom, right, before it's dissolved. It's just the instant before we stir it and it dissolves. That's like a concentrated, one balloon that's concentrated with gas atoms, right? It doesn't like to just sit there when there's room in the solution for the sodium chloride to dissolve. So considering the solvent to be like a vacuum and the solute to be like a gas, it is overwhelmingly likely that a solute will dissolve if there is no energy of interaction between the particles, like the ideal gas case. So they're saying in the event that sodium chloride had no interaction with another sodium chloride, well, it would easily just disperse, just like a gas molecule. So, but we know that this isn't entirely true, right? Just like we know that the ideal gas equation isn't totally true because atoms can interact together, we know that a solute is going to have interactions together. So in sodium chloride, we know that sodium and chloride have that ionic force together, yes? Well, in the crystal, there are lots of ionic forces. One sodium cation is not interacting with just one chlorine anion, right? It's interacting with lots of chlorine anions. So there are lots of forces holding them together. It takes energy to separate one sodium chloride from another sodium chloride. We know that there are forces between them. So there are several energies that we have to consider. If I take water and sodium chloride, how do I get that sodium chloride to dissolve? Well, there are solute-solute forces. So the solute being sodium chloride to sodium chloride. Solute-solvent forces, so sodium chloride interacting with water. And there's solvent-solvent, water interacting with water. For me to get a sodium chloride from another sodium chloride and a water from another water together, I have to break a water-water interaction, a sodium chloride interaction, and then put them together. So you can imagine, let's say perhaps for a moment, that sodium chloride and water weren't miscible. They didn't like each other. They do, I'm saying that they didn't. It would be hard to break sodium chloride, which has a strong bond, and water, which has a strong bond together, and put them together if they didn't have a good interaction. These are the sort of things we need to consider. So if all of the forces were the same, if water had an equal energy of interaction with another water, and sodium chloride has an equal energy of interaction with another sodium chloride, and they had an equal energy of interaction with each other, then they just dissolve because entropy is increasing. Back to statistics. We have that increase in randomness. So the enthalpy, delta H dissolve, measures the sum of the three interactions. We must first separate the solute molecules, so that sodium chloride, and the solvent molecules, that water and water, and then mix the two together. So water has a network of hydrogen bonds, we should know this by now, that keep forming and breaking randomly in the liquid. So that's something I have to consider. When I break that water-water interaction, it's not just dipole-dipole, there's also the hydrogen bonds. We already know that water has a strong intermolecular force, right? So I have to break that first, and that costs energy. Other molecules that can form hydrogen bonds are then quite soluble in water. So, yes.
Can you slow down a little bit?
Oh, sure. Am I going too fast for you guys?
Yes.
You want me to back up?
Yeah.
A few slides? Just tell me when. When? When I heard it? Okay. All right. This is my first time. Yeah. Be gentle. So let's see. We're at energy interaction. Let me go back a couple slides and go through it again. Okay. All right. What's funny is I heard Muhammad went through quickly, and I was like, not me. Not me. Ain't gonna happen. All right. Heat this way. Gas this way out. Do you want me to just? What time is it? I got plenty of time, right? All right. 11:24. Wow. 24 minutes have passed, and I know that's most of the slides. Keep it down. So Muhammad went through most of my slides. That's my excuse. But we do have some sample problems at the end, some review questions for the exam, and we're going to go over those as well. And that'll take up some time. Or we can just have light conversation. I'm down for anything. I haven't been keeping track of the website. Has he gotten the other ones up yet? What was that? So the slides for up to lecture 4 are on? And we're at lecture 6, right? That's true. So he hasn't been here all week. So I anticipate he'll have the slides up. I'll make sure to ask him about it too. Yeah, good. I'm glad we had this talk. Okay, so we have it's only 11:24. All right, let's go through this again. All right. Okay. Too far? You guys are never happy with anything. Okay. We're good? No, I'm getting mixed signals from everyone. That's more? Okay, we're going to start here. Anyone has a problem, just get out and leave. Okay, we're going to start here. I'll go through it again a little more slowly, all right? Okay. So counting configurations. Remember, we're talking about these two containers. Hey, yeah, right, yeah, thank you, okay. This is all on video, you're making me look bad. Anyway. Okay, so we have two containers, right? And what did we do? We took one container that had 6 atoms in it, and we opened it up to another container that had 0. Just by statistics, we know that this is going to become equal. As I mentioned before, when we open up this container at first and we had 6 on one side, they're crashing around randomly, and they're just going to, by statistics, eventually find this hole and make their way to the other side. This is going to keep happening until we have an equal amount going from one side to the other and an equal amount coming from that second side to the first. It's an equilibrium. We have 3 on each. One switches to the other, another switches back, and so forth. But this is only with 6 atoms. So this is only with 6 atoms. So in this distribution, where we have 5 to 1, 5 on one side and 1 on the other, this configuration label is 5 to 1. 5 in the first container and 1 in the other. And its statistical weight is 6. There are 6 ways that I can put 5 on one side and 1 on the other, right? And if I want to do a 1 to 5, so 1 on one side and 5 on the other, that also is going to have a weight of 6. But it'll be 5 on this side and 1 on the other. So we have to consider what are all the possible ways for me to arrange these atoms. So, with 4 and 2, continuing that line of thought, we have 15 different ways, where 4 are on this side and 2 here. So green, blue, blue, purple, right, yellow, red. You just switch one of them. Keep the red on here, but switch the yellow with that light blue one. That's a whole different configuration. A whole other possibility for these atoms when we consider their randomness. Continued on, there are 15 different ways to arrange second here. 4 and 2. Those have 4, 2. That one has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Oh, error. I'm glad we redid this. That was not even caught. I'm sure this is why you were all confused. So in any case, ways to put 4 and 2, 15 different ways. And then for the 3 and 3, there are 20. You can do this yourself. When the numbers are small, you can just write out all the different combinations and add them up if you like math. I do. So for that 3 for 3, there are 20 different ways to color the atoms. But then those configurations of 2 to 4, 5 and 1, and 0 and 6, as I mentioned, they have the same weights as 4 to 2, 5 to 1. There's another typo. I didn't write these. So 2 to 4 and 5 to 1. First container has 2, second container has 4. That has the same as the first container having 4, and the second container having 2. This one, 5 and 1, has the same as 1 and 5. And then 0 and 6, 6 and 0.
Shouldn't they all have the same weights?
What?
Why wouldn't they all have the same weight for doing the 6 atoms at a time?
Why wouldn't each one have the same weight? Which, let's go back. So 2 and 4, 5 and 1, 0 and 6, right? Why don't each of 2 and 4, 5 and 1, 0 and 6 have the same weights?
Yeah, they're all 6 atoms total.
They're also, so let's go back to the images. So compare 6, 0, right? If the atoms are moving around totally randomly, there's only one possible way for me to have 6 and 0, with 6 in the first and 0 in the second, okay? If I go just to 5 and 1, and we'll go back and forth between this, there are 6 different ways to do this. So if I just take a snapshot of this gas, right? Totally random, if I took 1,000,000 snapshots, I'm going to get a statistical distribution between whether my snapshot sees 0 and 6 or 5 and 1. If it's totally statistical, based on what are the chances of me seeing 6 and 0 or 5 and 1, I know that 6 times more often, I'm going to see 5 and 1, just because that is more likely. There are more configurations for this than for 6 and 0.
So I think kind of going off this question, that they don't mean actually like weight as in the traditional sense we mean it. It's more of like lightness in this case.
Yeah, I must have said it too quickly earlier. This weight is not a mass. Yeah, sorry, I was blazing through before. Okay. This weight is not a mass at all. This is a statistical weight. Okay. It's saying contributed to all the possible configurations. This is just a number that represents what chance do I have of seeing the situation. So going back by 1, this has a weight of 1. There's only one chance of having 6 and 0. One possibility. Going on to the next, I have 5 possibilities of having 5 in the first and 1 in the second. And so this has a statistical weight of 6. It's 6 times more likely to see this than 6 and 0. Okay, does that answer your question?
Yes.
Okay, thank you for bringing that up. I didn't realize that people had missed that. Okay. The weight thing. So, 4 and 2. So you can see, as we're just talking about, you go 5 to 1, right? There's 5 possible configurations. Take that a step further. Go to 4 and 2. Here are all the possible ways for me to write 4 in 1 and 2 in the second. There are 15 different combinations. So if the atoms are totally at random, going to have some configuration, I have 15 different ways that show me this exact arrangement. Remember, these atoms, all the different colors, they're still just one atom. They're all just krypton. So if I took a picture of this right now, I wouldn't be able to distinguish the top left from the bottom, from any ones on the right. It would all look exactly the same to me. And so I would count that as another one of my 4 and 2. That's a second count. And if I keep doing that, snapshot, 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 over and over again, I'm going to have 15 different possible ways to see 4 and 2, but only one possible way to see 6 and 0. And that's where this comes from. That's where the statistical reasons for equilibrium come from. So for that 3 and 3, we're just taking the same thing to the next configuration. there are 20 different ways to color those atoms. And then you were asking why they don't have the same weight. So the configurations, well, no, I already answered that question fully, I suppose. So the configurations, 2 in one, 4 in the other, 5 in one, 1 in the other, and 0 in one, and 6 in the other, those have the same weights as flipping your diagram. So 6 and 0 has one possible configuration, and 0 and 6 has one possible configuration. Together, I have 2 possibilities of ever taking that image and seeing 6 in either with 0 in the other. So the total configurations that are possible are 64. So let's think about that 6 and 0. I take a snapshot. There are 2 in 64 chances that I will take a snapshot with 6 in one and 0 in the other. It's very small. And if I have, I'll go to the next page that has the, here you go. And 50 out of 64 of those times, if the atoms are moving randomly, we'll look and see that 4 in one and 2 in the other, or 3 in one and 3 in the other. Because what I'm doing is adding the 20. So remember, 20 corresponded to 3 and 3, right? So 3 and 3, plus the chances to see 4 and 2. So 4 and 2, that was 15, right? So 4 and 2, 15. 3 and 3, that's 20. And 2 and 4, which is another 15. That's how many, right? That's the sum. 4 and 2, 15. 15, 30, 50. 50 out of 64 times, I'm going to see one of these. And 14 out of 64 times, we'll see 6, 0, 5, 1, 1, 5, or 0, 6. So the 6 and the 0, right? That contributes 1. The 0 and the 6, that contributes another 1. The 5 and the 1, that contributes 6. The 1 and the 5, that contributes 6. Total, 14 out of 64. So the chance of me seeing very few on one side and more on the other is very small. Only 14 and 64 when I only have 6 atoms. Since the number of possibilities increases exponentially, the chance of me having most of a gas on one side and little gas on the other, that becomes completely insignificant, and we don't even consider the possibility. So they spread out because it's more likely for them to be found equally. If I take 1,000,000 atoms, the chances of me seeing 500,000 on one and 500,000 on the other, that's incredibly high. Of course, give or take a couple atoms. Who's counting, right? Likewise, if you're a gambling person, we roll a pair of dice. The most likely outcome is to get a 7. Quick tangent. Went to Vegas for my first time a few weeks ago for my anniversary. Bet $100. Lost it all. Never do that again.
Congratulations.
Thank you. I know. It was roulette. I'm stupid, I know. Who plays the roulette table? You're going to lose. I was up 60, and then 10 minutes later I'm down 50. I don't know how it works. Yeah. When we have large numbers of atoms, a nearly even distribution is overwhelmingly likely. So, considering that solvent to be like a vacuum, as we were mentioning before, and the solute to be like a gas, it is overwhelmingly likely that a solute will dissolve if there is no energy of interaction between the particles, like in the ideal gas case. So let's picture this again. We have that beaker of water with a bunch of sodium chloride just sitting in a mass. It's not likely for that sodium chloride to just sit in the mass as long as those interactions are the same, like the ideal gas case. No energy of interaction for sodium chloride. However, we know that there are forces between atoms in condensed phases. As I was mentioning earlier, we know that sodium chloride has an interaction with energy. And we know that in a sodium chloride crystal, that sodium chloride is interacting with several other sodium chloride. And it's hard to break them apart. They have strong ionic forces that require energy to break one sodium chloride from another sodium chloride. So there are 3 pairwise energies to consider. Solute, that's the sodium chloride in this case. So breaking apart sodium chloride from another sodium chloride, that takes energy. The solute and solvent, When I take that sodium chloride and water approaches, where we have interacting forces, and in the case of water and sodium chloride, that's a positive energy, it's favorable, so those attract. And I have solvent-solvent, so water and water. Like I mentioned before, water, we know, has very strong interacting forces. So I have water, it takes energy to break that apart. So I have two unfavorable energies, breaking water away from water, breaking sodium chloride away from sodium chloride. And I have a favorable energy, taking sodium chloride and interacting with water. And if that interacting energy is strong enough, it can overcome the energies that I'm having to break. So if all of the energies are exactly the same, then breaking a water apart from a water and replacing it with sodium chloride, well, that's no different energy-wise, right? If the interaction of water with water, I break it apart, but then that sodium chloride comes in and I get that energy back, well, then it doesn't matter. And it's just going to be statistics, and it's going to dissolve because we're increasing that entropy. Delta S is greater than 0. If this were the first time going through it, would that be a good pace? Better? Okay, all right. I'll keep that in mind. So the enthalpy, delta H of dissolving, measures the sum of those three interactions. We must first separate the solute molecules and the solvent molecules, and then mix the two together. And if that is a good energy, it will happen naturally. And if it takes more energy to do that than not to, it's not going to happen. So water has that network of hydrogen bonds that keep forming and breaking randomly in the liquid. Other molecules can also form those hydrogen bonds, and then are quite soluble in water. So let's go back to what I was saying a moment ago, right? I have to break water from water, and I have to break something else from something else. Let's say ammonia, right? NH3. Well, I know NH3 has hydrogen bonds, right? So when I take that ammonia and bring it closer to water, I know they're going to form strong hydrogen bonds. This increases that interaction between water and that solute. So I think it would be more likely to dissolve. And in this case, it would. Ammonia is soluble in water. So ethanol, methanol, ethylene glycol, they're miscible with water, right? What do they have? Ethanol has a hydrogen bond. Yeah, it has an aliphatic region, but it also has that OH group, right? And that forms hydrogen bonds with water. And so it can dissolve. Same thing with ethylene glycol or methanol, forming those hydrogen bonds. On the other hand, a long-chain alkane, like hexane, with H atoms only on carbon, it's not going to dissolve very much. We get two layers, right? Like salad dressing. Or if you're just in your lab and you have oil and water, right? So let's talk about this for a second then. If we have oil, we'll just say it's hexane, okay? Hexane and water. They don't mix. We all know that. Why don't they mix? Hexane, what kind of forces does it have? Intermolecular forces, I mean, right? Just dispersion mostly, right? It doesn't have any H bonds. It doesn't have a dipole. It doesn't have any ionic contributions. It's just dispersion. Hexane doesn't hold together very well. That's why it has such a low boiling point. Water, however, holds together very powerfully. It has strong hydrogen bonds. It has dipole-dipole forces. It holds together. So when I try to put the two together, I have to break a hexane-hexane interaction. That's easy, because its dispersion forces aren't very strong. But I have to break a strong water-water interaction. Now, if the hexane-water interaction were powerful, that would be okay. But it's not. Hexane doesn't have any hydrogen bonds it can give to water. It's not a dipole, so it can't interact with water's dipole very well. It's just sort of like dispersion forces or an ion-induced dipole, that sort of thing. It's a weak interaction. And so you're not going to break apart strong water with weak hexane because their interaction is also weak, so they separate. So we're on to some practice problems. Exam time is next week. Remember what Dr. Shaka said, oh, it's not time to leave. We have some problems. I mean, you can leave if you want. I'm not keeping track. But let's see here. What time? We got 11:43. So we got plenty of time. There are about 5 questions here. And the exam is Tuesday. It's going to cover chapters 5 and 11 plus the review 1 through 3. But he'll probably focus on 5 through 11, I'm sure, but you just in case you need to know 1 through 3. So we'll just go through some exam questions right now. Well, not exam questions, some review questions, and we'll see how it goes. What factors influence the boiling point and the melting point of a pure substance? What influence does molecular shape have on the liquid range? So I think what I'll do for these problems, especially because we have plenty of time, is I'll just give maybe 30 seconds for you guys to think about a problem, and then we'll go over it together, all right? So go ahead and just think about this for about 30 seconds. I'll try to keep quiet. It's very hard for me. I like to talk, but I'll try. It's very hard. All right, so let's talk about this. What factors influence the boiling point and the melting point of pure substance? And how do you affect that liquid range? So we know the boiling point is going to be influenced by molecular forces. Boiling point is how much energy do I have to put in to get those to break apart from each other, right? Put them into the gas phase. So very strong interactions are going to increase my boiling point. Water has very strong interactions. It's got a high boiling point. Hexane does not have very strong interactions. It's going to have a low boiling point, right? So we consider ion-ion, ion-dipole, dipole-dipole, London dispersion forces, and hydrogen bonding. If you ever forget what those mean, go look in the textbook. I really encourage people to read the textbook. I read the textbook, look where I'm at, up here teaching you. It works. So the melting point is influenced by similar factors, but packing is very important. I don't recall if Dr. Stock ever mentioned packing in his lectures. But how well layers and layers of your compound fit together influence how closely they can get together and how strong that interaction is, right? So we know that if I just took an ion-ion, right, like a positive and a minus charge, the closer I bring them together, the harder it is for me to pull them apart. Same thing with solids. If I have things that pack really well together, then when it comes time to try and break them apart, to go from the melting point to get in the liquid phase, well, it's going to be harder to pull them apart into the liquid phase if they're packed really tightly together. If something doesn't fit at all, well, there are a few, it's not as able to interact as well, and you can break it apart a little bit easier, and that's going to lower its melting point. So a molecule that is round or symmetrical may have a high melting point because it fits together well. So if a symmetrical molecule has only dispersion forces, it may also have a low boiling point and so have a small range over which is a liquid. Some molecules like CO2 have no liquid range at 1 atm pressure. They sublime. Again, a phase diagram, you should be getting very familiar with these. Pressure versus temperature. We know that with dry ice, with CO2, that's minus 78.5 degrees Celsius. That's at about 195 Kelvin, right in that range. So it's unfortunate this graph doesn't show that place. But here we're in the solid form, dry ice, right? So at 1 bar is around 1 atm. At a temperature of around 195 Kelvin, we're in this region right here, where we would be a solid. And as it warms up, we enter right into the gas phase instead of the liquid phase. So we need almost 60 bar pressure to have CO2 be a liquid at room temperature. So if I increase this pressure, right, let's say I'm at 100 bar, and then I increase the temperature, then I'll enter into the liquid phase, and eventually into the supercritical fluid. Yes? What was that?
Can you just find a question from one of the lines? What do they mean by
Wait, this slide or the one prior?
yeah, this one.
Okay.
What do they mean by still having small range over which is liquid? What do they exactly mean?
So if something has a melting point of 0 degrees Celsius, like water, right, and a boiling point of 100 degrees Celsius, that's a 100 degrees Celsius range. Okay, that's not a big range. You can liquid. They're saying that when things have very, very, very a small amount of intermolecular forces, sometimes it can't even stay as a liquid very well. Once you melt it, it goes into the gas phase pretty quickly. So you would have a very small range, let's say at 10 degrees. I don't know what, well, for CO2, there's no range at all, right? It doesn't stay a liquid. But they're saying there will be a much smaller range, like 10 degrees Celsius, something like that, over which it could be a liquid. I can't think of any examples that have a really small range, but except for this one maybe. So, are there any more questions on that problem? All right, I don't see any hands. Okay. So a gas mixture has 90% argon by volume and 10% helium by volume. You may treat these as ideal gases. If low pressure effusion through a pinhole is used to try to separate the two gases, what would the percentage of helium by volume be after the process? Now, we're not going to sit here while people work out the whole problem. Take a minute to think about it, write out whatever you want, think about how you address this problem, and then we'll go over it together. Okay? All right, let's talk about it. So we're using Graham's law, page 208. It tells us the relative rates of effusion through a small orifice go like the inverse square root of the masses. So we'll look at this for one moment. That is R1 over R2. Those are rates, not radii. The rate of the first thing going through a small hole divided by the rate of the second thing going through a small hole equals the mass of the second thing over the mass of the first. Take the root. So let's talk about it for 1 second. Does this make sense? I have argon and helium. Argon is very heavy. Helium, not so much. I put them into a container with a small hole, right? If they're at the same temperature, which they should be, which one's moving faster? Helium, right? And we have our own equations that tell us that. Helium's moving very quickly. It's bouncing around very, very fast. Statistically, it has a better chance of getting through that hole because it's going to hit that hole more often, right? The size of the hole doesn't have anything to do with the difference in size between argon and helium, right? Argon is still infinitesimally small compared to the size of the hole, so it's only based on the mass. Helium is bouncing around. It's going to hit that hole more often and get through. So if we take this and we plug in those masses and take the rates, we can find out the ratio of the rates. We can't solve R1 and R2. We're taking the ratio. Helium's 4 grams per mole, and argon is 40. And so what this means is that the ratio, that relative rate, and remember, that's R1 over R2. The ratio is 3.162. That's where we're saying helium will go through that hole 3.162 times as fast as whatever argon does. We haven't insinuated any kind of rate or a time. We're not saying how long this happens for. We're saying that for 1 moment, the rate is going to be 3.162 times the rate of argon. And so if we set that rate of argon diffusion to 1 in any units, we know that the rate of diffusion of helium is going to be 3.162 times whatever that rate is. And hence after 1 stage of effusion, so we could have this in seconds or hours, whatever, it depends on how accurate you want to be. After 1 stage of effusion through an orifice, we'll have relative numbers of atoms. So argon, at some rate going through, I'm going to have 0.9 of whatever my units are going through. Helium, there's only 0.1 worth of helium versus argon. Remember, it was 90% argon and 10% helium. And so the 10% of helium at 3 times faster a rate, I'm going to have 0.3162 amount of something coming through. And so what happens is total, I have the 0.9 plus the 0.3162, that's how much got through, and this is how much helium there is. That's now 26%. So we increased from 10% helium to 26% helium. I believe that Dr. Shaka used uranium as an example for this in the first lecture on ways to separate things. It can be quite useful, although they don't use uranium isotope separation by that method very often anymore. They use centrifuges. So, oh, any questions? I didn't realize that was the end of the answer. Say again? Yeah, sure. We're all just writing down, or do we have questions? Or? What? Oh, sure. The one with the actual question on it. Yes.
26% was the percent in the chamber.
In the second chamber, so we have one chamber and then another. In that second chamber, right? We let stuff transfer over. That's now 20%, or excuse me, 26% helium. Now, something to consider is that rate doesn't stay the same, right? In that first stage, we had 90% argon and 10% helium. In the after we've let that go through, we know that my second container has 26% helium. Why is that important? That means that in the first container, I now have even less helium by percentage than I did before. I had 10% before. Now, whatever the amount is, it's going to be less than 10%. So if I keep letting that going, the difference in rate, which was 3.162, that's going to start decreasing. Because as I get closer and closer to there being almost no helium, there's going to be more argon going through than helium. So,
your question asks what volume in the original container after the process.
gas, 2 gas phase, what would the percentage of helium by volume be after the process? Where are you looking at? Because the last line?
Yeah.
Oh, it was saying the percentage of volume is going to be 26%.
That's the new.
That's the new container. Whatever went through is now 26% helium. Okay?
On the previous slide, the equation for all of this, R1 over R2 and then M2 over M1.
Yes. So this makes sense, right? Let's say 1 is helium. Okay? So the rate for helium is going to increase faster and faster relative to argon as the mass of argon, or whatever my second one is, gets heavier and heavier versus helium. So let's pretend it's not argon for a second. When this is argon, we have 3.164, right? So M2, 40, over M1, 4. Take the root, 3.164. If I made M lead, right, something really heavy, let's just say something 200 grams per mole, okay? That now is 200 over 1, and take the root. That's going to mean R1 over 2 is now really big. Because helium is so much faster than whatever that really heavy gas is that I put in there. Does that make sense? Okay. Right there. I couldn't hear that whole thing. Oh, it just makes the math easier. If we had a real situation, we would want to know exactly how much argon we have. This is a demonstration of using ratios to compare relative rates. We just said that, here we go. We say that R1 over R2 is, there you are, 3.162, okay? So I'm pretending that whatever the rate of argon is, I just call that 1. And I'm saying relative to that, so R2 is 1. If the ratio R1 over R2 is 3.162, that lets me say that the rate of helium transfer is 3.162 times whatever argon is. I think I'll have to limit that one. Well, we've had plenty of time, right? Wish there was a clock besides this guy. 11:58. Its class gets out at 12:20. We got a few more questions. If you have more questions on it, come down and ask me afterwards. Okay? so we'll move on. Did anyone want just a moment to write something down now real quick? You got it? Okay. All right, so another practice problem. All right, recall that a van der Waals gas follows the equation of state as follows. I'm not going to read through that. Remember that the ideal gas equation is just PV equals nRT, and here we've said, well, PV equals nRT is great, you know, but it's not fantastic. So we've added in these correction factors, a n squared over v squared and minus nv. So where the gas-specific parameters a and b depend on a gas, if for xenon we have a equals 4.192 liters squared atm per mole, and b equals 0.05156 liters per mole, then what is the volume of 1 mole of xenon at 5 degrees Celsius and 2 atm pressure to 3 significant digits? Now, I'd like to take a moment here to point out something about units. So, if you were just looking at this, you think, well, what are the units of A? I know what the units of N are, right? N squared, it's moles, so that's going to be mole squared. And the V, that's liters squared. For me to add two things together, they have to be the same units, right? And so automatically, I know the units of A. Because for A n squared over V squared to equal ATM, A has to be liters squared to cancel this out, ATM, so that you have ATM, per mole squared to cancel out the mole squared there. That's just a quick way to address what are the units in a situation. Similar to NB, for volume equals liters, NB also will have to be liters. And so B is going to be liters per mole because N is mole. So mole times liters per mole gives you liters. Excuse me. So go ahead and take a moment to try and find the, where was it? And what is the volume? Try and find the volume of 1 mole of xenon at 5 degrees Celsius and 2 atm pressure to 3 significant digits. Okay. Tip, don't try and solve for V in that equation. You're going to make a quick guess using the equation that you have. That's not quite as accurate as that one, but it'll let you almost get the answer. So Dr. Shaka earlier in the quarter, remember he has the get really close and then punch in the calculator a couple of guesses until you're spot on, right? So don't try and solve for V. All right, so let's go ahead and flip on over. So, first thing, as Dr. Shaka is fond of telling you, remember to convert Celsius to Kelvin. Keep everything in the same units. His advice is to use PV equals nRT to first guess almost the right answer, and then you're going to nudge your way to the correct answer. So, figure out NRT, and do not round R, because we need the accuracy. So something he keeps on harping on in the class is don't round too much, right? If he asks the accuracy, don't think at the end, just, 3 digits. Just make sure at the end I have 3 digits. If you cut out certain digits earlier in the problem, it's going to ruin your accuracy down in the end. So you have to keep that many digits all the time. So in this case, we're using as many digits of R as is practical. Going out to 4 is plenty good. That's going to give us all the accuracy we need and more to get our 3 digits in the end. So figure out nRT, don't round R, and that equals 22.8243 liter ATM. From here, so we started with the ideal gas estimate of the volume when we begin guessing. So, or use any method that works for you. You can graph it or whatever, but make sure you get the 3 digits correct. Verify your answer by substituting it back into the equation. Okay. All right. So he's saying, well, we know nRT. If we go back to the full equation, nRT doesn't have A and B in it. We're not making any assumption by just solving for nRT. So we can do that right off the bat. It's this side with the more complex equation that causes us grief. So we can start with just PV as a quick guess, which doesn't have the A and B in it. And then we can, in his words, scoosh our way over to the correct answer. So if we let our function of volume equal 2 ATM plus 4.192 liter ATM per volume squared times volume minus 0.05156L. So let me go back for a second. What we're doing is we're taking, there we go. We have this equation, right? We're trying to figure out the volume. So we can easily make this a function that depends on volume. And that's just pressure plus AN squared over volume times volume minus NV. So let's go back up to that slide. So our function, pressure plus the 4.192 liter squared ATM over V squared, so that's AN squared divided by V squared times V minus the NV. So he just figured out these numbers and put them in, and this is our function for V. So if we plug in values of V in liters and see what we get, our starting guess is, using the ideal gas equation, just V equals nRT over P. We should all know that, definitely. And that guesstimate is 11.4121 liters. So we set up a table, okay, where this is the volume in liters, this is the function of volume in liters ATM, our target value, which should be 11.4121, and then our little comment on that value. So when we do the ideal gas law, we have 11.4121, or excuse me, the target value is 22.82. When we do volume based on the ideal gas law, that's 11.4121. And the function, when we plug volume into our function, is 23.0867 liters ATM. Our target value, which is nRT, right? We're trying to get PV equals nRT. Ideal gas law wasn't good enough. Van der Waals equation has A and B. We're taking that first guess, putting in the function. We know that nRT is 22.8243, and we're trying to see how accurate we are. So volume 11.4121 gives us too big a value. So we go a little bit smaller in volume, right? 11.2. Well, put it into our function, and that's a little too small. So 11.3, we put that in, and we're just scoosh big. His words, not mine. I think scoosh is a weird way to describe it. I'd rather use tiny. So 11.25, that's a bit small. So depending on what accuracy we're looking for, we know that the answer is in between 11.25 and 11.3. So rounding to 3 digits like it asked, that's 11.3. Practice. You have a question?
Yeah, sorry. How did we know to divide nRT by pressure? I think the last time we turned this, we just plugged in nRT.
So, I gotta go all the way back, don't I? Okay, so, Van der Waals equation, accurate. Ideal gas equation, not so much, right? We can replace all of this with PV, and that's the ideal gas equation. So, going forward, your question was, why does volume equal nRT over P? That's just using the ideal gas law, right? Did that answer your question? I feel like I missed something in your question. Was there something that I didn't get to? Okay, it did? All right, good. Good. Any questions with that? No? I think there's one more problem. Let me just go ahead. Yeah, so we have an X-ray diffraction question, and we have 12:08. All right, we got 12 minutes. I think this is the last problem. An X-ray diffraction experiment using copper K alpha X-rays, so that's just describing what level of X-ray it's at, of wavelength 1.54 angstrom on a pure metal crystal gave a first-order Bragg peak at an angle theta equals 14.17 degrees. If you're not familiar with this, go read the book. They have a quick and simple explanation on diffraction and how this is working. So we have a metallic crystal. It's just layer upon layer, a simple cubit probably, of metal. So the incident angle of radiation is 14.17 degrees, and they tell us the wavelength is 1.54 angstroms. Assuming the crystal has a cubic lattice and that the peak arises from the atoms on the corners of the cube, what is the dimension of the unit cell? If the structure is simple cubic, what is the radius of the atom? What further information would you need to identify the actual element? So I'll go ahead and give you 1 minute to work on this a little bit. Excuse me. And then we'll work over it. Yeah. It's funny to be down here and actually see people like sleeping with their heads so much back. Like, I mean, I just want to like laser point them in the eye, but obviously I can't because their eyes are closed. All right. All right, real quick before we go over it, I want to ask, you guys up there in the balcony, is my camcorder still going? It is? Okay. This is my first time teaching a lecture with this many people. Never done it before. Can you all just give a shout out to my mom and dad? I'm going to send it to them. So on 3, we're all going to say, hi, Mom, hi, Dad. All right, just for me. Do it for me, do it for me, do it for me. Okay? 1, 2, 3. Hi, Mom. Hi, Dad. Love you. Okay. So, all right. Oh, my wife. Hi, Daniela. Hi, Daniela. Thank you. Okay, let's talk about this. Let's talk about this. All right. So we have a first order diffraction, and that's code for n equals 1 if we're thinking about this equation. Okay? 1, normally this would be n. N equals 1 in the Bragg equation. Hence we have 1 times the wavelength, which we already have because they gave us that, equals 2 times d sine theta. They gave us theta. What we're solving for is d. So let's go back 1 second here because there was an assumption that was made and we didn't talk about it. When it says that assuming the crystal has a cubic lattice and that the peak arises from the atoms on the corners of the cube, what that's saying is d was a measure of the distance in between my slit where the X-rays are being diffracted, right? It's not always the case that one set of layers makes that diffraction. We're making that assumption. So if I just solve for d, well, maybe that comes out as 10 angstroms, and that could correspond to 5 or 6 layers. We made the assumption that it's from the first layer. And so d is just the distance in between the 2 corners on that point. Okay? So 0.3. So if we solve for d, that's 0.3145 nanometers. And for a simple cubic unit cell, this is 2r. Remember, we were trying to solve the radius of the atom. If it's a cubic lattice, I have atoms at all the cubes, and they're touching each other, right? If they're touching each other, and I know the distance in between the middle point of those 2 atoms, because they're right at the corners, then I know the radius of each atom, because I know the distance, and the radius is just 0.157 nanometers. So cut that in half. So we're trying... Oh, sorry, my bad, guys. My bad. We're just writing down? Do we have questions? Questions so far? Just writing down? Okay, all right. Let's see what we have. All right, moving on. I'm hearing a lot of murmurs, which I don't know what that means, yes or no. So we were trying to find the, well, let me read the end of the question again real quick. We were trying to find the mass, right? Yeah, what further information do you need to identify the actual element? So what do we need to identify the element? Well, we already have the volume, right? We have the radius. What's the last thing that we would need? For a simple cubic cell, there is 1 atom per unit cell, right? That's because at each corner, we have 1/8 of that atom contributing to the unit cell. 8 corners, that's 1 atom. So we can figure out how many moles there are in a cubic centimeter. So if we then knew the density of the material in grams per centimeter squared, then we would know how many grams there are per mole. And that lets us, of course, identify the atom. Because we know the grams per mole, well, we just look over at the periodic table, and that's all we need. So, and this is very, very true. Real X-ray experiments are, of course, a lot more complex than this. Nobody takes crystal structures of things that are just one element anymore. They're incredibly, incredibly complex. So, there's density, yeah. So we need the mass. Any questions? Huh? Well, why don't you go ahead and start going? You can come down and ask me.
It's just a kind of general question. Do you know anything about the notes? We're allowed
Anything about what?
Is there any like restrictions?
Okay, so notes for the exam, they can only be notes that you've taken in class. So you can't go outside of class, write a book, come bring it in. You wouldn't want to do that anyway. How are you going to have time to look at it, right?
So we can't like say take a list of the equations and research, or you simply have to
You